Hello everyone, this is the video lecture for Calculus 3, section 16.3, vector fields and potential functions. Let me go ahead and give you a formula here. We got our f vector is actually equal to grad little f. Well, there's your formula for the whole section. No, there's going to be a little bit more. They're going to occasionally talk about being conservative, and I want to show how a vector field could be conservative. There's basically a formula for it. If your f, which is basically called p and q, or we would say like x and y essentially, it would be conservative if your dp dy is equal to dq dx, del d, partial derivatives there. If this is a true statement, then it's called conservative. And essentially, if that's true, you can actually find the potential function, and later on it'll mean something else in other sections and stuff like that. So it's just a little mini test that will occasionally come up in this section, so we can always just go back to that quick little formula for it. All right, let's go. So 16.3.007. So my f vector is y e to the x plus sine y, e to the x plus x cosine y. Okay, so first off, is this conservative? Can I go and find my potential function, my little f, essentially? And if you can't, then you would put something like DNE or something like that. It kind of depends on the problem, but let's go and see, is this conservative to begin with? So this is your P and this is your Q. Notice I'm not using X and Y normally here because, well, first off, it's not your R vector, but second off, you actually have X's and Y's integrated into it. So I've got to use a different letter. P and Q sounds fine. So this one here, we're going to take a derivative in terms of y, and notice that we'll have e to the x, and then sine goes to cosine. Okay, this guy over here, del q del x, dq dx. In terms of x, we got e to the x, doesn't change, and then this guy here, x is going to go away and leaves a cosine. These are equal, so I would say yes, conservative. Great. Okay, now, because of that, and again, if they had a little checkbox, you click conservative, keep moving, but I'm pretty sure on this problem they're going to want the potential function. If you can get it to be conservative, we can, so here we go. The formula, yet again, is my capital F is actually equal to grad F. And what they're wanting is what is little f here? What is little f given that I have a cap f? And so you have to remember that grad here is basically a derivative. You're doing derivatives of each term, making it into a vector. What we're doing then is we're trying to go kind of like backwards. How do you get rid of this derivative? Well, in a weird way, you're trying to integrate, and this is definitely bad math here, but you integrate to get your these guys to cancel, and you got your little f. Okay, so we're integrating my f, basically, but I want to show you how that works in specific, okay? So what I'm going to do now is something kind of weird. I'm going to integrate each component according to the variable in which it's sitting. So that's an x component, so I'm going to integrate it in terms of x. So I know that there's not such a true thing, I guess, as like partial integrals, but if we were to do it, this would be it. So we're going to integrate this guy here. I want to integrate in terms of x, so then you can see the integral of this guy is going to be a y e to the x. Doesn't change. Right here, there is no x, so essentially you add an x to it, and plus c. Remember this plus c, we don't often do it here in Calculus 3, but plus c is important here, and I'll tell you why more so in a minute. Let me do the other integral, so I'm going to integrate this q term now, but now I'm going to integrate it in terms of y. So again, integrate this guy in terms of x, integrate this guy in terms of y. So it's just a little weird. I know it's kind of like an anti-gradient, I guess you can say. You're going backwards on the gradient understanding. So instead of taking a derivative, you're taking an integral, but of each term. So again, I have integral in terms of y, so I got y e to the x, and here my cosine will make into a sine, and then plus c. The plus c's are actually very important. Look at our two answers right here. You see these guys right there? What I'm saying is that this here is my potential function. This here is my potential function. Sometimes they're not always the same exactly, but they will have common components. Notice that my common components are here and there, and well as c, I suppose. What I'm going to say is my little f actually is, my potential function is, oops, that's a plus sign, I guess all of the important aspects that you've seen in any of the boxes. Of course, this is granted that it's going to be conservative to start with. You will have overlap. If it's not conservative, I don't think it's going to overlap and you'll just get a mess. So this was actually a pretty nice way that it actually made the same in both cases. That is not always the case, but you're looking for commonalities and they should be very similar in a way. So the C is actually very important because this C right here could mean something potentially that this box has that I didn't already have up here. And the same thing, this C here could be something that was hidden in this box that wasn't initially in that box. They are accounting for differences, essentially. So when I say my little f is this, if I were to do grad f, I would hope that I get my cap f vector. And you can go and do it, and I'm sure it'll work. But we're done here. That's the answer. I think that doing more than just one is really going to help you understand how this works together. So let's do some more examples. So I got cap f is equal to 6 plus 2xy squared, and then I got 2x squared y. And they're saying that, it's kind of interesting, or they say that my curve for this f is the arc of a hyperbola y equals 1 over x. If you ever seen this, we often think, oh, that's a reciprocal function. Yeah, but like turn your head to the side a little bit, and you can see actually you got a hyperbola right here. See that? It's kind of interesting. So we got a hyperbola essentially, and they're wanting to go from the point 1, 1 to 3, 1/3. Okay, so 1, 1 to 3, 1/3 is going to be down this way. So this little, I guess you can say like this little arc right here on my hyperbola. This one has a two-part process. So part A is saying find your potential function. I am assuming then that they're saying that it's conservative so that I can actually do this. And then part B, they want to find f.dr, which we were doing in the last section. So let's find our potential function. I'm going to essentially, instead of taking my gradient, I'm doing like an anti-gradient, I guess you can say, of my f vector. So I'm going to integrate each component according to the variable in which it should be lying. So again, x and then y. So integrate this in terms of dx. So I get 6x plus, and you can see that we're going to have a square here and divide by the 2. The 2's are going to cancel, so x squared, y squared, and again plus c. I'm going to integrate the other guy here, 2xy, x squared y, dy, so this one in terms of y now. And again, y squared over 2, the 2's are going to cancel, leaving x squared, y squared, plus c. Okay, perfect example of how plus c is actually very important. This plus c might have had something that this box here didn't have. It didn't. There was nothing here missing, I guess you can say. Or I'm sorry, there's nothing added there. But this C actually is right here that 6x. It's that 6x. The reason why is because you're integrating in terms of y. Basically, this is like a c sub x, not as terms of derivatives, but I'm saying it's a function in terms of x. I wouldn't have ever known it by simply integrating in terms of y. I just don't know. It would not come up. It's kind of weird. Like, I guess you're taking a derivative and an integral, and so you're missing a part. Just as a quick mini example, let's just say my f was equal to, I'm just going to make something up here, 2x plus 3. And I say, well, then take a derivative. And so we get 2, right? That was easy. And then I say, well, integrate that derivative in terms of the x. And we get 2x plus c, right? Well, notice that I'm missing the 3. Like, where'd the 3 go? That's the thing. Your c is that 3. So that's what I'm getting at on the side here, is that when we integrate in terms of x or y, we're not knowing the full picture of what's going on. That's why we have to do both of them. Hopefully they match up. Obviously, x squared, y squared, x squared, y squared. There are some matching ups, and then some other kind of functions that might be in one or the other. Putting them all together, now that we see them all, it is the x squared, y squared, and also the 6x. No need for plus c's. That's not really what you're wanting for your potential function, okay? And so that's part A, essentially. You're done there. Very good. Keep moving. So it now says find f dot dr over that curve. So this is different. You could go back and try to make a parametric equation going from 1, 1 to 3, 1/3 along the line of y equals 1 over x. You can do that. You could set up, like, I don't know, there's t equals 0 right there, and this guy right there, that's going to be a t equals 1, and you go through all the process and blah, blah, blah. I don't want to go down that road because I want to tell you why we did part A to begin with. There's got to be a reason for this potential function to exist, and especially to do it before part B. Well, there's a new formula that they give you here. This is actually A to B. Those are going to be like... those are just points, I guess you can say. So from A to B of grad f dot dr. Notice that I'm replacing this guy here with grad f. Sounds good. Okay, great. Well, now, if you kind of look at it, and we had discussed this a little bit ago, I'm taking the integral of a derivative, and basically these guys are going to cancel. You can't just simply throw that in there. But the idea is there that those are going to cancel each other, kind of, and so you have f r at b, and then minus f of r at a. Okay, now I don't want to make this too weird, but essentially this is going to end up being like this chunk here is, in this particular case, a point. Nope, sorry. That's actually 3 1/3. And this here is 1, 1. Your terminal point minus the initial point. But of course contained inside of the f function. So my potential function, I'm going to plug in my f at 3 1/3 minus, and then I'm going to plug in my f at 1, 1, my little f here. So plugging in 3 1/3, you can see that we got 3 squared and then 1/3 squared, and then plus 6 times the 3. Over here on this side, we got 1 squared, 1 squared, plus 6 times the 1. So 3 squared, 1/3 squared, they actually cancel, make a 1 there, plus 6 times 3 is 18, and then over here minus, we got 1, so minus a 1, and then minus, because I'm distributing here, minus 6. So the 1s here are actually going to cancel. 18 minus 6 is actually a 12. There you go. So given that we have a new formula for it, you don't have to find that pathway exactly. You're simply just going to find the terminal and initial points, plug them into the potential function, and you get the answer. So kind of a neat way of going around that without having to do extra math. And I think the rest of the problems are going to try to emphasize that. So I'm going to show you here. The next one is yz, xz, xy plus 12z. And they say, oh, this is going to be a line segment from 1, 0, negative 2 until 4, 6, 1. Right now, they're not as blatant about it, but the next problem in particular is going to give you a way of seeing this as like path independent, where as long as we're going from my initial and getting to my terminal, I should be good to go. All right. Now, I'm not going to go too far in that right now, but just know line segment from here to there. And so we're going to be using the potential function just like the last time. So part A, they're wanting my potential function. Again, I'm assuming that's conservative. If it's not, we'll quickly find that while trying to find the potential function. We're just going to get a big mess. So as of now, everything should be fine there. So I'm going to go ahead and integrate in terms of x, and we get x, y, z, and I'll put a plus c in there. The next one, xz in terms of y. So you get x, y, z plus c. No big deal there. And then xy plus 12z in terms of z. Well, then xyz. And then when you're integrating this guy, it's squared over 2 to 2 is going to cancel with a 12 to make a 6. Z squared plus c. Notice here that I'm trying to look at all of the pieces that are important. Your plus c's are essentially accounting for that missing component, that missing piece there. So then xyz and then plus 6z squared should be my potential function. Therefore, in the next case, they're saying, oh, we'll now find f dot dr. But we already know that this is going to be my potential function at R2, or terminal, and then at f of R1, or my initial. So terminal minus initial. Plugging in those points, again, we have, going back up, 4, 6, 1. So I'm going to literally say 4, 6, 1, and then plus 6 times, and then that was a z, so that would be a 1 squared. Minus, now plugging in my other point, which was 1, 0, negative 2, so 1, 0, negative 2, 6 times negative 2 squared. Sorry, this is a little bit weird right there. So, just doing the math now, we got 24 plus the 6. That's a 0. It's going to cancel. So this minus sign comes over here. Notice that we have already 2 negatives make a positive, but that minus in the front is going to keep it a negative. 4 times the 6 is another 24. And so these guys cancel out, leaving you with a 6. So there you go. Next problem. 163025. So yet again, they're wanting the potential function, and your integral of that's basically the same thing as last time. It's kind of weird. Let me go ahead and write this out. I got integral 2x e negative y dx plus 2y, this is using parentheses now, minus x squared e negative y dy. Now, this is just kind of weird looking. We're going to, of course, talk about it here in a second. They say C is any path from 1 to 0 to 4, 1. So from 1, 0 to 4, 1, any path. Again, they're trying to say you can, as long as you're going from initial to terminal, you can take a straight line. You can get all squiggly with it. You can kind of do a little roundabout thing. As long as you're going from here to there, you're going to get the same answer in the end. And that's good for us. So let's go and find our, because it's conservative, so then I'm going to go ahead and find my potential function, use a quick little formula, and get the answer. Now, my question here is, what is f? That's what we're missing here, you know what I mean? Normally I just go right to my f, and I can integrate and all that kind of stuff here. Well, we're going to have to, of course, understand this in two different parts. Notice that I basically have here and here the Q and P parts of my f. I'm saying that we have it already kind of there. They just wrote it in a different way. But if you notice that they're trying to already integrate for you, you see that in terms of the term, in terms of the variable in which it should be sitting, they kind of are telling you to just do those integrals. So we're going to do these integrals here in terms of the dx dy that they have already given us. It's already pre-constructed, essentially. So let's go and find it. What's my integral of this guy here? In terms of x, I'm going to get x squared over 2 to 2, so I'm going to cancel, make a square, x squared e to the negative y, and then plus c. Integrate this next one. We got 2y minus x squared e to the negative y dy. Okay, in terms of y, we're going to get the y squared over 2 to 2's cancel, make a y squared. Here, I have to integrate in terms of y. Kind of strange how you're integrating e to the whatever. Well, it's the same as going to be as a derivative. That negative sign is going to basically be tossed out to the front, making this into a positive x squared e to the negative y, and then plus c. Notice that this is positive and this is also positive. It's actually very important. But that c there actually was the y squared the whole time. My potential function then is equal to y squared plus x squared e to the negative y. So that's my potential function. And of course, now we're going to find my integral of essentially f dot dr, and that's going to be f at r2 minus f at r1, or those 2 points that they have given to me. Again, this is going to be a 4, 1, and this guy is 1, 0. So, plugging in to my potential function, I have 1 squared plus 4 squared e to the negative 1, and then minus, over here I got 0 squared plus 1 squared e to the negative 0. Okay, so we got basically 1. Here I got a 16 over e, kind of a little different there. 0 is going to go away, but the minus sign, of course, distributes. Notice that we have a 1 and a 1, and so we just get a 1. 2 1s are going to cancel and make this guy your final answer. Keep going. 16, 3, 0, 29. So this time I'm given an f is equal to x to the 5th, y to the 5th. And they're saying we're going from 0.10 until q 3, 3. Isn't that funny they use p and q all over the place? For your vectors, for your components, for your points. Anyways, it says find the work done. And really all it is here is going to be f dot dr. Again, that's no different than what we normally do. I put in my notes here that we could make a line, a straight line out of this. And with that straight line, we can have x in terms of t. If you remember how this works, x in terms of t, y in terms of t. This is actually my r. And then I would have my r prime and the magnitude and find it out and plug it in. Well, we could do that, of course. But, or we can use the potential function. So let's go ahead and do that because I think it's easier. Integral of x to the 5th power dx. We here have x to the 6 over 6 plus c. Integrating the other one, y to the 5th dy, that's y to the 6 over 6, and then plus c. This c is that guy, this c is that guy. So my potential function is basically both of them put together. There you go. All right. And what I did is I factored out the 6 to the front, but that was not required. From there, I'm going to go ahead and plug in my answer. So my work done, that integral f dr essentially, is going to be f at r2 minus f at r1. We already have those points that they had given me originally. This is now 3, 3. This here is 1, 0. And so, plugging it in, I got 1, 6. I'm just going to factor that to the front, makes it a little bit easier here. We got 3 squared plus 3 squared minus 1, 6. Now I'm going to plug in a 1 squared plus 0 squared. So 3 squared and 3 squared, we got 9 plus 9 is 18. 18 over 6 is just going to basically be a 3, I believe. No. Hold on. I messed up here, guys. It's not a square, is it? look, it's a 6 power. It's a 6 power. Look how easy it is to mess up this kind of stuff, right? Okay, those are 6 powers. Okay, I thought something was looking a little weird for a minute. Okay, 1 6 times and then 3 to the 6 plus 3 to the 6th is going to be way bigger, is 243. And over here, the 0 doesn't matter. That's just a 1, so minus a 6th. And so when you do this in a calculator, because, well, I don't want to do that by hand, you get this answer right here. So there we go. So apparently they were asking at some point if it was conservative or not. Maybe. I'm not entirely sure. I don't really do that formula very often. The reason why is because I just assume that it's going to work. So I have a little note here, like, you know, before we're done, I just want to talk about this again. So conservative. Throughout this section, they're going to ask if this f vector is conservative or not. And we've got to test it and say yes or no. And if it's not, then we've got to do something else. But again, I've already shown you the formula here for this. So it's dp dy should equal dq dx. This is for the 2-dimensionals. The 3-dimensionals are a little bit bigger than that. It's actually a pretty big formula for the 3-dimensionals, but I'm not going to go into that right now. Anyways, so we're supposed to be testing to see if this actually works or not. If it does, great. If it doesn't, then you would just say DNE or something like that. And so I'm just going to go back and do one more problem. This is 003, so I'm kind of going backwards here on this one. I got my f vector is xy plus y to the 4. I got x squared plus 4xy. And so I want to show you that this one's actually going to be not conservative, therefore it's DNE and all that kind of stuff. So this is, again, my P, and this is my Q. So dp dy, when I take my derivative here in terms of y, I'm going to get an x plus 4y cubed dq dx. And I start doing my derivative here, I get a 2x, and then over here a 4y. Notice that these are not the same. So not conservative. And basically you can't do my little trick that you can do any kind of path to get to that same point from P to Q. I don't want to use the same words. From point 1 to point 2 or initial to terminal. You can't do that in this particular case. What they're going to ask you to do to find little f, basically you still have to put something in there. On WebAssign, you're going to put DNE because it's not conservative. You can't really do this. DNE, just walk away. You're done. So this is we're done with that problem. But I want to kind of show you that you don't always really have to go and find if something is conservative or not. Notice that I did it maybe twice when the homework does ask you to do it a little bit more than that. But I want to show you what's going to happen if I were to attempt to find little f. So, like, what would happen if I actually started to integrate this stuff? And what does it look like? How can I tell that basically I should just walk away and not do anything about it? So, when I integrate this guy, I'm going to get the x squared over 2 times the y, and then plus y. Oh, no, that's an x there. X, y to the 4, and then plus c. So there's that one. The other one right quick, I got this x squared, and then 4 xy dy. So integrating this, I got, in terms of y, x squared y. And in terms of y here, it's going to be the y squared over 2 to 2's cancel and make a 2xy squared plus c. Now let's just kind of go back and forth on this just a tiny bit, okay? So this guy and this guy are not the same. They look kind of similar, but, well, you know. Look right here and right here. You have x squared times y, and you got x squared times y, but this one has a half in the front. You have a half in the front, while here the variable in the front's a 1. You can't use a c, especially with x squareds and y's kind of like coupled together, to be able to account for that. So that's a dead giveaway, in my particular opinion. in fact, also you're seeing that this C cannot be here because it's not just in terms of Y's. And this C here can't be this guy because it's not just in terms of X's. It just does not make sense. And so that's why we simply say D and E. It's not going to work. And you walk away, okay? But again, I like, in particular, these scalars are not the same. So that's definitely a giveaway in my opinion there. Okay, I think that's it. So, yeah, we're done with that section. Good. Thank you very much. Have a great day.